Good evening, everybody. I'm Marty Geyer, your gsp295 instructor, and welcome back to Week 2's video lecture. I want to give you a brief overview of the ADT structure for lists. So without further ado, let's start. So first part is, what is an ADT list? What is a list? Well, I think you guys already know this answer because you've been building them in your other courses. Just simply an array, a linked list, is a type of list data structure. It's anything that holds data, basically. It's a very simple fundamental structure. In fact, we're going to use it later on to build more complex data structures. You can build one data structure on top of another, which is kind of why we start with the simple ones and build from there. So here's an example of a simple list. Notice this is not particularly ordered. We start with the unsorted list, which is just the same thing as a list. A sorted list is a list that is actually sorted, but we won't go there just yet. So 1, 4, 5, 2, 9. I'm just going to give examples in integers here. In your lab, you're going to work with strings, but kind of obviously any data type will work in a list. So you're building these simple data structure, abstract data type to hold any type of data. So any class, any personalized thing you can think of is valid here. I'm just using int as an example. So you already know this. You've done this before, in fact, but you haven't kind of probably formalized it. So what we're doing here is formalizing into a set of operations that you need to have to make it an abstract data type. And those operations are listed here and in your book, of course. I'll run through them real quick. So make empty. Make empty is a simple operation that just bookkeeping clears the list. All right. So for example, for arrays, all this is set the length to 0 and you're good to go. This is usually very, very simple. Is full, is this a list that is currently full or not full? And this depends on your implementation on how you do this, of course. But this is a simple way to tell whether we can add more elements. Get length of the list. So this is a simple operation to get the total number of elements that you have currently in the list. For example, this would be 5 on this length here. If we took one out, it would be 4, etc. Retrieve item. I wanted to stop and say something real quick about retrieve item with regard to the lab that may help you. So in your book, this is written kind of convoluted as void retrieve item, which takes a parameter item type pointer and a boolean found. This is a convoluted way of saying they don't want to use any return values in the book. They want to pass in a pointer that they're going to then fill with the item once you find it, and a boolean value indicating whether or not it was found. This is, I mean, you're welcome to do it this way. Your book is just kind of being very strict about how it formalizes things, but I don't particularly care in this class. So you're welcome to do this the more kind of programmatic way a lot of times that people think of it, and return a boolean value as to whether or not it's found. So true, false, whether you found something. If it's false, then you don't actually look at this item, and if it's true, then you do. And then pass a string pointer or int pointer or whatever to the actual data that then is filled. That's also a perfectly fine way to do it. You can do it any way you want. You can think of a third way if you want, so long as the basic idea is there, that you have some indication of whether or not the item was found or not, and a place to actually return the item. Otherwise, of course, retrieving it isn't actually retrieving it. So back over to here for a second. So insert item. This will insert into the list. Delete item, remove from the list, reset list, and get next item. These two down here are separated a little because these are iterative operations. So oftentimes you want to iterate over a list. I'm going to get like an iterator if you've done that before. This is a way of formalizing this. So you can get the next item, and that will simply loop through the list. So at the beginning, when you reset the list, the pointer is pointing here. You run get next item, it'll return 1. And then if you run it again, it'll return 4, 5, 2, 9. It simply iterates over the list until you call reset to put it back. And that allows somebody interfacing with this ADT function you're creating to iterate over the list. So these are kind of the basic operations of what you need to do to build an abstract data type list. Now, there are two basic ways to implement this, and your book goes through all this in detail, so I'm going to skip most of it here. I simply want you to understand the high-level concepts and how they impact everything else. So an array is a simple one that I'm sure you've all done, and hopefully many of you have also done a linked list implementation, which is a simple loop-de-loop, with these are being the next pointers. Here is how I've represented them. So you can implement in these two ways, or you could even think of some other way of implementing. Remember that implementation is not important to the ADT itself. We're simply defining the operations. That being said, as was pointed out by a couple students, yes, we're doing implementation. The lab's actually going to have you do this, so you do need to be able to do an implementation. For the purposes of the discussion, the purposes of these video lectures, I'm talking at a higher level, so I'm going to refer more to the ADT functions and how they impact implementation. So the interesting thing first we have to point out to follow up with our discussion last week about big O and the runtimes is how fast are these functions. Notice that a lot of these things are constant time. There's a table, by the way, on page 184 for the unsorted list operations of how long they take. This is a simple constant operation because it just does some cleanup. However, for a linked list, cleanup may be cleaning up the entire list if you're resetting it. So it might not be. It might be order of the length of list, which is n, or it might be constant. Is full. This is just a simple, usually you're going to track a number of items in the list, so this is always going to be constant time. So I've written these over here for you. So for array implementation, order 1 for make empty, and order n for linked list. Is full is always constant because you're just returning whether or not it's reached the maximum value. Get length is also constant time operation because you're keeping track of the length inside of the list operation somewhere. Retrieve now is a little tricky because you don't, since the list isn't sorted, you don't know where it is. So the best you can do is to look through every item of the list in order to tell whether or not it's in there. Because assuming you were looking for, say, 10, you wouldn't know that it wasn't in there until you look through every single one. So on average, you're going to look through every single one, which is a order of n operation. It doesn't really matter whether you do this with array or linked list, you have the same problem. For inserting item, now this is easy. This is always constant time because we don't care about the ordering. So insert a new one and just boom, put it there. Or if it's first one here, put it here, put it here, put it here. It's just simple, make a new node and add it. And delete item is also going to be order of n operation similar to retrieve. And the reason, as your book explains, is that you have to do a retrieve first in order to actually be able to delete it. So you can't delete it unless you found it. In fact, it might not even be in here. So if I'm looking for 11 and it's not in here, then I won't actually be able to delete it. If I'm looking for 10, I might have to go all the way through the list before I can delete it. In addition to that, that's it for unsorted. So for unsorted, you just have to find it. Once you found it, you can remove it pretty easily enough. Remember, with linked lists, you can simply rearrange pointers, so it's an easy thing to do. With an array, you can do a couple of different things. You can shift the array down, or you could just mark that there's a spot empty, or what have you. But even if you shift the whole array down, which is also an order of n operation, you still haven't made the operation any worse. It's still order of n. You can't do any better than that with an unsorted list, with these two implementations. And iteration isn't really important because it's not an operation that you're doing over looking for a particular thing. You just simply iterate over the list. So that's kind of an overview. Now, sorting the list is the next chapter, and sorting the list changes some of these. I'm going to go back over here. Some of these big O operations. When you do a sort on the list, no longer is it easy to just simply insert. Now you have to insert and readjust things because you have to insert in the right spot. So if you have this list that's sorted, you want to insert 2. You have to make a node for it here, clean it up there. That means you have to find it again, and now you have to insert it. You might have to, for an array, push everything down. I'm not going to go into the details of all this implementation because it's in your book, and it's a good thing to read through, and we're going to discuss in the discussion forums. But sorting does change the big O's, and there's another table in the chapter that will explain that to you. There's also extensions to lists, such as circular linked lists, doubly linked lists, that have different purposes as well that we'll go over in the discussion. But I wanted to give you kind of a brief overview, and there it is for lists. And please let me know if you have any questions, and we'll see you next week.